All right, go ahead, Dr.
Okay, so I'll begin and then I'll stop after I'm done. And then end the session, eh?
Yes.
Hello? Okay.
Okay.
Okay. Okay, welcome back. Let's continue with our discussion on arithmetic circuits for zero knowledge proofs. As we said, we are in this arithmetic circuits, we are learning how to write circuits, how to come up with circuits that we then be using in our zero knowledge proofs. I remember that for us to be able to write, to verify computations in zero knowledge proofs, we need to understand the knowledge of arithmetic circuits and then the knowledge of R1CS, which we then be looking at after this topic. So we had begun looking at this arithmetic circuits for zero knowledge proofs, and this is just a continuation of what we had already begun. I had already said that arithmetic circuits provide a structured way to express computations or computational problems as polynomials. And we saw an example of how our equations would then be written as polynomials. And those equations are the ones, the system of equations are the ones you're referring to as arithmetic circuits or the circuits. So today we want to advance this notion of writing arithmetic circuits, and this time we'll be looking at some examples that are used in applications, in real life applications, the three coloring with an arithmetic circuit. And then we shall be looking at how to verify if a list is sorted. So the knowledge of finding out if a list is sorted, we shall see how important it is in zero knowledge proof, for instance, because we'll be seeing how to write a circuit that gives us a range of values. Because in zero knowledge proof, sometimes we want the verifier to just to give us a value within a specified range without necessarily having to reveal what the value is. So then the prover is supposed to be aware that is supposed to verify that the value has been given is indeed in that range, so that it's not given values outside the range. Now, so we'll be looking at these examples. These examples are very important in zero knowledge proofs. So we begin by looking at the example of the three coloring with the arithmetic circuit. So what we'll be looking at this point is where we are given a region that is subdivided into different subregions. A region subdivided into different subregions, of course, neighboring each other. And we want to color each of the subregions with a different color. So we only have three colors, but we want to ensure that non-neighboring subregions have the same color. So that is what we'll be looking at. So we have three colors and we want to, so let me just try to draw something here just to illustrate what I'm saying. So for instance, supposing I have this region and I have subregions. I have these subregions. I want to ensure that each of these subregions has one color. So supposing I have red, I have blue, and I have yellow. These are the only colors that I have to color. I want to ensure that this region receives maybe blue, and that blue must be, this other region should not receive blue. If this one receives blue, the neighboring regions should not receive blue, should have a different color, and so on. That's what we'll be doing. So supposing this one receives blue, we expect that this one will be maybe red, and maybe this one another color, and maybe this one. So we'll be coming up with the circuits, that can enable us to color these regions differently. So that is what the three coloring notion is about, just to ensure that each region has a different color from the other region. So no two neighboring regions have the same color. That will be our mission in the first exam. Now, so we'll be using the arithmetic circuit. And of course, from the start, we said arithmetic circuit has an advantage over the Boolean circuit. When you're dealing with a Boolean circuit, you will see that each region would require 3 Boolean variables to represent one color. And they will also require to have constraints that ensure exactly one variable is true. Now, that is if you go to, that is how you write Boolean circuits. But now when you go to the use of arithmetic circuits, we would find that this is a bit complicated. The Boolean one is a bit complicated, but this one for the arithmetic circuit is not as complicated, because we would just assign a single signal, X, and this X could be 1, could be 2, or 3, where 1 would stand for one color, maybe blue. We assign blue maybe to be called 1, and we assign, let me say, green to be 2, and maybe yellow will be 3. So supposing I have these 3 colors, and then I would assign each of these colors a number, 1, 2, 3. That's why I've said we assign a single signal X per region. So every region is assigned a single signal, and the signal is just a member of this set, 1, 2, 3. So in fact, when I give an example, you'll see this one will be very clear. When I give an example, you'll see how we'll be able to assign these colors and, of course, shade each of the regions differently if they're neighboring. Now, so the circuit is here, or the constraint. So what we want to do, we've assigned the colors 1, 2, 3. So we just want to say that would come up with this equation that 1 raised to minus x multiplied by 2 minus x multiplied by 3 minus x should give us 0. 1 minus x multiplied by 2 minus x multiplied by 3 minus x should give us 0. And x is one of these values. X is either 1, 2, 3. So you can see, for instance, if this x is 1, if this x is 1, then what we then be having will be 1 minus 1, then 2 minus 1, then 3 minus 1. And the result, the first bracket is 0. So whatever is here multiplied by 0 will just be 0. So you can see, then if x is 1, this equation will be satisfied. If x is 2, again, you would see from the second bracket, we have 2 minus 2, which will again be 0. If x is 3, then you can see that again, from the third bracket, we would have 3 minus 3, which again would give us 0. So that means this equation can only be satisfied if the x values are either 1 or 2 or 3. If x values are 1, 2, or 3, that is only when this equation is satisfied. So this is the equation we then be using to assign those colors. Now, I just want to take an example of Australia map. And these are the regions. Of course, I've already colored them. And this is what we're supposed to be doing. So you can see I've only 3 colors here. You can see these are only 3 colors, but I've ensured that no neighboring region have the same color. This is what this notion is all about. That once we are given a region and we are asked to color the region and we are only given 3 colors, we should be able to cover every part of the region and ensuring that no neighboring regions have the same color. So with the 3 colors, we are able to do that. So we can have either 3 coloring problem or the 4 coloring problem. So if you have 4 colors, for instance, you can also do that with 4 colors, and you can do that with 3 colors. That is, you don't require more colors, you just require 4 colors or 3 colors, and you're able to color the neighboring regions separately, differently. Now, so these are the regions, these are the 6 regions you have from that map. You have the Western Australia, you have the South Australia, of the Northern Territory, and so on. And we want to color each one of them differently without having 2 neighboring regions with the same color. So I have my 3 colors. I want blue to be 1, red to be 2, and then green to be 3. That's just as we said, we give those colors numbers. Now we had already said this, that we would have 0 should be equal to 1 minus the color for the first territory, multiplied by 2 minus the color for the second. Okay, if you are considering the first territory, then it will be 1 minus t, which is that territory, the color for that territory, then 2 minus t, and then 3 times minus t, where t then represents that territory. Now, in our case, we have 6 territories. So since we have 6 territories, then this is what the coloring problem would have, what this translates to. This then translates to 0 is equals to 1 minus WA, where this one is West Australia, Western Australia, and so on. So 1 minus that color, Western Australia, then 2 minus the color for the Western Australia, then 3 minus the color for the Western Australia. Then you could also have 1 minus the color for Southern Australia, and so on. And then Northern Australia, and so on. So that is all what we do. Then, of course, we have assigned those colors as 1, 2, 3. So it's important to note, to understand how then each of these territories would have 1 color. But this is the equation we will be using. This is the equation we'll be using. Now, so we just want to modify the above equation to ensure that there are no 2 regions, neighboring regions, that would then have the same color. To ensure that we would not have 2 neighboring regions with the same color, we modify that equation slightly. So just before we modify it, let's look what the possibilities of 2 regions with the 2 different colors. Supposing this is the colors for first region, and these are the colors for the second region. So if the colors of the first region are 1, 1, 1, we can have a possibility of 1 and 1, the first region and the second region having the same color, 1 and 2. Remember that 1 was blue. 1 was blue. I think There was what was 2? Let me just go back and find out. Okay, red was 2 and then green was 3. Red was 2. So this is 1. Red was 2. And then green was 3. So these are possibilities of 2 neighboring regions. So we have 2 neighboring regions. So the possibility is that the first region could be red, no blue, and the other one could be blue. So if that is the case, then the product will be 1. But remember, this is invalid because we don't want 2 regions, neighboring regions, to have the same color. So this would then be invalid. Now, the other possibility is that the first region could be red, no, could be a blue, and this other region be red. So the product would then be 2, which is valid because these 2 regions have different colors. You can see this is red, no blue, and this is red. The other possibility is that this could be blue, and then this one be green. So in this case, then the product will be 3. Again, this is valid. This one was not valid. So this is valid. This is valid because we want 2 neighboring regions to have different colors. Now, we could also have a possibility of the first region being red and the second region be blue. So in that case, the product would be 2. And again, this one is valid. Look at this other possibility. This is red and this is red. So these are 2 neighboring regions with the same color. The product is 4 and then is invalid. Now, this is red and this is green. The product is 6, valid. This is green and this is blue. The product is 3, which is again green. This is green, valid. This one is green and this is red. The product is 6, valid. But look at this case again. 2 neighboring regions with the same color, green, green. So this one is invalid. So what we then get from this table is that whenever 2 regions have the same color, a case of 1, 1, the product will be 1, and this will be invalid. The other case will be 2, 2, which the product will then be 4, and this again is invalid. And the other case is 3, 3, 2 regions with the same color, 3, 3. This will be 9, and again invalid. So whenever the product is 1, 4, and 9, it then means that we can never have that combination. We can never have that combination. We can never have a combination of the same colors, red, blue, blue. We can never have a combination of red, red, and green, green. So whenever the product is 1, 4, 9, that combination is not valid. But now, if the product is 2, or 3, or 6, it means the combination is valid. A case of 1, 2, or 2, 1, 1, 2, or 2, 1. 3, the case of 1, 3, 1, 3, or 3, 1. And then a case of 2, 3, or 3, 2. So those are the only cases when you can now see from this table the cases when the colors are valid and when colors are invalid. And so we then use this table to make slight amendment to that equation, just to come up with the equation that will then ensure that any 2 neighboring regions have 2 different colors if we were to color them. So that is, I'll be taking you step by step through this so that you then get to understand what we are doing. Now, so just a recap of what I've already talked about from that table. I've said that if two adjacent territories have the same color, their product will then be either 1, 4, or 9, and this product will be invalid. It will mean that we can never have those colors. We can never have two regions with the same colors. Now, if they have different colors, then their products will be 2, 3, and 6, as we saw from that table. Now, so remember the equation. This was the equation. The equation was for the assigning colors. The equation for assigning colors was 1 minus territory multiplied by 2 minus territory multiplied by 3 minus territory. This was for assigning colors. Now, the equation for ensuring that no two neighboring regions have the same color is now this. You can see this is a product as we've been looking at, as we've seen from that table. We've just modified this equation a bit, but this equation is still using it. We are still using it for assigning colors, but then we now come and use this one for ensuring that we do not have two regions, neighboring regions with the same color. So these are the products. So you can see this 2 is coming from this set. From this set, the set where the products are valid. So these products are 2, 3, and 6, and those 2, 3, and 6 are what you now see here, are the ones you're seeing here. So whenever we have, supposing x times y is 2, then it means those two regions have two different colors. If x times y is 2, that will give us 0 here, because the first bracket will then become 0, and then whatever is in the other brackets multiplied by 0 would still be 0. So it will mean that the two colors you've assigned are valid. The other case is when x times y is 3. If x times y is 3, then we'll have 3 minus 3, which will then be 0 in this bracket. Another case is here, where x times y gives us 6. So that we have 6 minus 6. Now, so these are the two equations we require to assign, to be able to, if you're given a region that has several sub-regions and you're asked to color them, each of the neighboring regions having the different colors, you would then use these two equations to do that. And that is what you want to do, therefore. Now, this is just a summary of what we've already said. Of course, telling us what we'll be doing. To fully constrain the system, to ensure that we have every region with a different color, so that two neighboring regions do not have the same color. We will iterate over all the neighboring territories and apply the above constraints, the above two equations that we just had. So we go through, iterate over all the neighboring regions and apply the two equations to see that we give every region a different color. So this is just a repetition. We've already said that if Western Australia and Southern Australia were two neighboring regions, and then this equation should be satisfied. where their product, the product of the two colors is supposed to be either 2, or it's supposed to be 3, or it's supposed to be 6. So it should be n of these, should be either 2 or 3 or 6, the product of those two colors, since these are two neighboring regions. And if that happens to ensure that these two regions have two different colors. Now, so how shall we move, ensure that these regions have two different colors? We begin by assigning one. Okay. So let me say these are the regions I have, and I want to shade them. Supposing this is my region A, B, C, D, E, F, G, H, I. Or to color them, I want to color these regions so that since B, for instance, since B neighbors C, A, and F, we would not have C, E, and no, this is A. B neighbors A, C, and, or you can see it's A. It neighbors A, C, F. It also neighbors, this is E, and then a D. So B is neighboring all these regions. We want to ensure that if B is blue, for instance, none of its neighbors is blue. None of its neighbors is blue. That's what we want to do. If B is assigned blue, we want to ensure that none of its neighbors, and we can see what the neighbors are here. We only have 3 colors. The one we are using, we've been given blue, been given red, and we've been given green. So supposing we assign blue color to B, we want to ensure that each of its neighbors, and its neighbors here are A, C, F, E, and D, none of them should have blue. So we would assign blue, and the blue was given color 1, was given 1. So after assigning blue to B, we would come to any of its neighbors. Let me call it C. So and then we use this equation. We just say 0 is equal to 2 minus blue times C multiplied by 3 minus blue times C multiplied by 6 minus blue times C. Blue times C. Now, but we've already assigned blue. We've already assigned this B color 1 blue. We've already assigned, okay, this is only blue, it was B. B times C, B times C, B times C. We've already assigned B 1. So just substitute 1 here. It will be 0 equals to 2 minus 1C, which is C, and then 3 minus 1C, which is C, and then my times, this was 6 minus 1C, which is C. This time, we may decide to assign C 2. We want to, because if you assign C to be 2, then we'd have a 0 in the first bracket. So assign C2. Assign C2. 2 was red. That means this one, if this one was shaded blue, this one would be red. This one would be red. Now you can, doing the same, you can assign this one to be green. This one to be green, using the same knowledge as above. You can assign this one. So this is blue, this is green, this is red. Now come to A and D. A and D. So A and D, just change the equation. This will be A, D. This will be A, D. This will be A, D. Just change those variables. But A, we already assigned A to be green. Green was 3, so you just substitute 3 where there's A, and so on. So I think we'll be looking at that example later. But that is what we'll be doing. That is specifically what we'll be doing to ensure that each of the regions has a different color. So of course, that's what I've done here. I've been looking at what neighbors what, and that is what I've done here. So for instance, when you look at these equations, you can see that West Australia's, one of the neighbors is South Australia. And so West Australia, South Australia, West Australia, South Australia. Of course, this one will be assigned color. We begin by assigning one of them a color. So we begin by assigning maybe West Australia color, and then you will come later and assign South Australia. And then West Australia also has another neighbor, which is Northern Australia, Northern Australia, Northern Australia. Those are the only neighbors for Western Australia. So this will be easy. Once you assign Western Australia color, using this formula, you can then assign Southern Australia another color. And since this one is already assigned a color, Western Australia is already assigned a color, using this formula, second equation, you can now assign Northern Australia another color. But the thing is, ensure that the colors are different for the two countries. Of course, if they're not different, then this equation will not be satisfied. This equation will not be satisfied. They must be different for this equation to be satisfied. Otherwise, it will not be satisfied. Now, let's just go through, and then we'll come and look at that example now, how we will then ultimately shade or color those regions. Now, so we had two constraints. The first constraint, we call it the coloring constraint, the one that gives colors. And what was the equation? The equation was 0 is equivalent to 1 minus t multiplied by 2 minus t multiplied by 3 minus t, where t is the territory. And the other one was, the other constraint was one that ensures that no two different colors, no two different regions have the same color. No two neighboring regions. The one that ensures that no two neighboring regions have the same color. And this is what we've been looking at, and it's here. Now this one is the first one, the color constraint. The color constraint that ensures that every region has one color is the color constraint. The one I was using T. So if the region is West Australia, then it will be West Australia, instead of my T. You remember I had written it as 1 minus T, 2 minus T, then 3 minus T. So T here represents the region. So if the region is Western Australia, then you replace T by Western Australia. The region is Southern Australia, and then you replace T with the Southern Australia. If it's Northern Australia, just replace T. So this ensures that every region has one color. Then we have the constraint that ensures that no two neighboring regions have the same color. No two neighboring regions have the same color. And that is the one we've just been looking at before we came to this page. And is here. This one ensures that no two neighboring regions have the same color. So if these are neighboring regions, they should not have the same color. And again, so we said what we do here, we iterate through all the regions. But you begin by assigning one of them a color. And then iterate through its neighbors. Then assign its neighbors colors. Then proceed to another region and so on. Now, so I think we are now familiar with that. This is just emphasis of what we've already talked about. But okay, this is now an example just to do the real thing. Want to do the real thing and assign different colors to that region, that map. This is now the real thing. Let's just do it. Now, so I have those regions. I assign one of them a color. I begin by assigning one of them a color. Then I use these constraints. I have this constraint and I have this constraint. This constraint that we've already said, it ensures that every region has one color. And this constraint we've already said, it ensures that no two neighboring regions have the same color. No two neighboring regions have the same color, so it ensures that. So let's now begin with the Western Australia, for instance, and we want to assign it one. One was blue, so we want to assign it one. So when we assign it one, we iterate through its neighbors and identify who the neighbors are. And the neighbors of Western Australia is Southern Australia. So using the equation for ensuring that no two neighboring regions have the same color, we do this. So it's 0 equals to 2 minus Western Australia times Southern Australia. Western Australia times Southern Australia. Western Australia times Southern Australia. But then Western Australia has been assigned A. Yeah, somebody called Krisang says, can you see a question? He says, if this is an example from the rare skills. Yes, this is an example from the rare skills on the coloring. Just seeing how to color. Supposing we want to color a region given a map. And we also use this in graphs, given graphs, and we want to color them. So we have the nodes, for instance, nodes of a graph, and we want to color so that no two neighboring nodes have the same color. So we also use it for coloring these graphs. But now the one you've mentioned is rare skills. Rare skills uses this particular example that I'm using. Now, so I want to color that region. So to color that region, I begin by assigning Western Australia color, and I've assigned 1 to it. 1 was blue. 1 was blue, so I assigned it blue color. After assigning it blue, I go through its neighbors and identify the neighbors. So one of the neighbors to Western Australia is Southern Australia. So using this constraint, we then substitute Western Australia by the color we've assigned it. We've assigned it 1. So when you substitute by 1, you then have 0 equals to 2 minus 1 multiplied by Southern Australia, and then that. Now, so I want to attack this first bracket, and I want this to be 2 minus 2. So if for it to be 2 minus 2, it means that this SA must be 2. So then that means the color I'm assigning Southern Australia is there for 2, which means red from above. We had already assigned red to be 2. So because if it's 2, then what that means that the first bracket will give us 2 minus 2, and that is 0. And the second bracket will be 3 minus 2. And the third bracket will be 6 minus 2. But the first bracket has already given us 0. So that means the entire thing multiplied by 0. This, whatever you get here, multiplied by 0 would still be 0. So that means it's true that we can assign SA 2, which is red. So you can now color it red. Now, so that's what we are doing. That's what we are doing. We've now found 2 colors on the map, and you color them. Then you find out whether Western Australia has another neighbor. Yes, you find out whether it has another neighbor. Of course, it doesn't. All the neighbors for Western Australia had only one neighbor, which is Southern Australia. So since Western Australia had been assigned 1, Southern Australia, using this constraint, we've assigned it 2. Now, Southern Australia is 2. Now find out the neighbors to Southern Australia. One of the neighbors is Northern Territory. Northern Territory. Again, use the same equation. Use the same constraint. Use the same constraint. 2 minus Southern Australia multiplied by the color for, of course, those colors we've given them numbers. For Northern Territory, then Southern Australia, Northern Territory, Southern Australia, Northern Territory. But Southern Australia has already been assigned 2, which is red. So you substitute 2 where the Southern Australia. Substitute 2 where the Southern Australia. And so if that is the case, then what do you get? You would then get this 2 minus 2 multiplied by Northern Territory, and again 2 multiplied by that, 2 multiplied by that. Now, so we want to get a 0. So there are various ways of getting a 0 here. One of the ways of getting a 0 is, okay, looking at what would be this color. This color could be 1. If this color is 1, then we have 2 minus 2. Yes, and here it would be 3 minus 2. And here it would be 6 minus 2. But this color can also be, you can also make this one 6, this part to be 6 by just letting this one be 3. If NT is 3, then we would have 6 minus 6. And the rest will be, what about this? This will be 3 minus 6. And this will be 2 minus 6. If NT is 3. If NT is 3. That's what you would then get. This will be 6 minus 6, which means 0, but this will be 3 minus 6, and this will be 2 minus 6. But since this last bracket is 0, multiplied by the rest, we still get a 0. Now, so let's choose on the last one. Let's choose on, since we've already assigned red somewhere and assigned blue somewhere, let's assign green, which is 3. Let's assign NT to be 3, so that we have NT being green. Now, so that is what happens. That's what happens if you are to shade a region. If you are to color a region and you have 3 colors, and I've said that if you have, if a region, for instance, there are cases when 3 colors may not work. There are cases when 3 colors may not work. For instance, let's assume that we have this region, and this region is bordered by that, is bordered by this, is bordered by that. So if one region is bordered by so many other regions, then 3 colors may not work. But then what happens is we also have the 4 coloring problem. 4 coloring problem. So what this 4 coloring problem says is that this one would solve any problem. If we have a region bordered with so many regions, 4 colors would then solve that. 4 colors would solve that. But in 3 colors, we have cases when it cannot work. But that is not the problem here. The problem is what we are looking at is, can we write equations to solve such a problem? That is our problem in this unit. Are we able to come up with circuits? Are we able to come up with constraints or equations that can solve a problem of this kind? And so we've seen how to come up with such a problem, how to solve such a problem. So that is the thing. The thing here is not that we have the 3 coloring problem may not solve other cases or not. The thing is, can we learn how to write equations that can solve such problems? Because we'll be encountering such problems in zero knowledge proofs. So whenever we meet them, can we then write equations? So that's what I did. This question, you just follow the reasoning. And when you follow this reasoning, it's the same thing. You then be able to shade the above region. You then be able to shade or color the above region. So I want us to, so after that, after all this working, then I came and settled on the following colors. That WA was assigned 1, which is blue in our case. SA was assigned 2. NT was assigned 3. Q was assigned 1. NSW was assigned 3. And the V was assigned 2. So you can see there was no neighboring regions that had the same color in this case. Now, why is this concept important? I would say that this concept is important because, for instance, in the case of zero knowledge proof, which is what we are interested in, this concept is important because it illustrates how logical constraints like those in graph coloring can be encoded into arithmetic relations. Now, we've been encountering such in zero knowledge proofs, and of course, after we are done with this topic and the next topic. Then we'll be looking at zero knowledge proofs and we'll be seeing how this one then comes in handy. Now, this note that the first color was just assigned arbitrarily. There was no formula for assigning the first color. That was just arbitrarily. We just said, let the first region that we're considering be blue. You can also say, let it be red, let it be green, and so on. There was no formula for choosing the first color. But once you've chosen the first color, the rest colors, you must arrive at them using those constraints. They are not arbitrarily chosen. You have to use the constraints, and you must ensure that the constraints are satisfied before you assign the color. Now, that is the first thing I wanted us to look at. That is the concept of three coloring problem. And the other thing that I want us to look at is verifying if a list is sorted. What I mean by this is that we want to verify if a list is arranged in some order. If the list is well arranged in ascending order or in descending order. That's what we mean by the list being sorted. So the list is arranged in some order. In ascending, you can see like my list here. I've arranged it in ascending this way. So you can see that A2 is greater than A1 or equal to A1. A3 is greater than A2 or equal to it, and so on. So they're increasing in this direction. They're increasing in this direction. So my list here is sorted. But now, how do you tell if your list is sorted? That is what we want to then be focusing on. That's what we'll be focusing on. How do you tell that the list is sorted? Now, so therefore, what is our goal? Our goal is to come up with the arithmetic circuit that would verify that a given list is sorted. That is our goal. Our aim is to come up, can we come up with an equation that will then be telling us that this list is well arranged? And again, this concept will be very much important to us in zero knowledge proofs. For instance, we have the issue of the range. You have the issue of the number between, let me say, 1 and 15, the range. We want to ensure if the value been given to us by the verifier lies within that range. That's one thing we will, how it then becomes important in zero knowledge proof. Because zero knowledge proof, when you are given, you have the verifier and the prover. And the verifier has to prove that he possesses some knowledge, X. Yes, he knows what X is. Now, it's upon us to know what range, which range does X lie? So that this verifier, although it's giving to us values that are not necessarily X, but these values are supposed to lie within a given range. They're supposed to lie within a given range, so that it's not giving to you a value that is very far from what you expect. So that is how this knowledge, this notion is important in zero knowledge proof. So we'll then be writing circuits that would be assisting us to tell if a given value is in the range that we expect. And so it will be verifying that. So that if the value is outside that range, again, you can tell that this verifier is lying. We can say that this guy is lying to us. Now, so our goal is to design an arithmetic circuit to verify that a given list is sorted. However, there is a small problem here. We began by saying that arithmetic circuits only have multiplication and addition. They do not have this sign greater than or equal to. Greater than or equal to. So arithmetic circuits do not have the sign greater than or equal to. So how do we then now write? We must get a way of going around this problem, because arithmetic circuits only have multiplication and addition as the signs. But now we are saying for the list to be sorted, it has to be arranged either in ascending order or in descending order, which means a value on the left, for instance, will be greater than or equal to a value on the right. Now, we've introduced the knowledge, another symbol greater than or equal to, which is not there. So there has to be a way of going around this. There has to be a way of going around this, and that is the way we want to look at. How do we go around this problem? So to go around this problem, we have to bring in the notion of the binary numbers. We have to bring in the notion of the binary numbers, and the binary numbers would then assist us to go around this problem. So that is what I'm going to. So it's here. So binary encoding as a prerequisite. This means is that for us to do this, for us to tell if our list is sorted, we must know how to convert decimal numbers to binary numbers, and vice versa. So to enable comparisons, of course, that is what we want to do. We want to compare values of the list. We want to compare whether the value on the left is greater than or equal to the one on the right. So to enable this comparison, we represent numbers in binary. A binary number is, this is how we write a binary number, like this, 1, 1, this is a binary number. The subscript 2 here tells us that it's binary. The base is always 2 for binary numbers. Now, this binary number is going to 3. This 3 is a decimal number. 3 is a decimal. How do you get 3? How do you get 3? Now, how do you get 3? Is 2 raised to 0 times 1 plus 2 raised to 1 times 1. This one is this, the least significant value here, 1. And this other one is this. And so 2 is the base. The base. So the first base, 2 raised to 0 times this first number. And then 2 raised to 1 times this number. So the first one here is 2 raised to 1 is 2. Of course, multiplied by 1 would be 2. And then 2 raised to 1, no, 2 raised to 0 is 1 times 1 would be 1. So that gives us 3. This is how you convert binary numbers to decimal. Even this one will be 5. How do you get 5? This one will be 1 times 2 raised to 0. This one will be 0 times 2 raised to 1. This is addition. And this will be 1 times 2 raised to 2. So the powers begin 0, 1, 2 from the right side, 0, 1, 2 from the right side. So this is 4. This is 0. And this is 1. That gives us 5. That's how we change from binary to decimal. But now from decimal to binary, we usually divide by 2 and note the remainder at every stage. Note the remainder at every stage. That's what we normally do. So let me just again show you how to convert from decimal to binary. or supposing I want binary, I would divide by the base. 2 is the base of a binary number. So I divide by 2 as I note the remainder at every step. So let me begin by this, for instance. 5. 5 is a decimal number divided by 2. So 2 goes here twice. But what is interesting to us is the remainder. The remainder is 1. Then 2 goes here once. But now the remainder is 0. Then 2 goes into this 1 0 times, and the remainder is 1. So you note these values from the bottom going up. So if you note these values from the bottom going up, you have 1 0 1 1 0 1. That's how you convert from decimal to binary. But of course, we can always write a code to do this for us. We can always write a code to do this for us. And of course, I've written a code to do it. I'll share the code for doing this conversion. Now, the only thing that is important to me here is not the conversion as such. The conversion is that each of these numbers, 1 1, each of these is called a bit. It's called a bit. So this is a bit, this is a bit. So these are 2 bits. This is a bit, this is a bit, this is a bit. So these are 3 bits. Each of these digits in a binary number is called a bit. And a bit is either 0 or 1. That is what is important to me here. And the other thing that is important to me is that the leftmost bit, and in this case, I'm referring to this is the leftmost, is called the most significant bit. The most significant bit. So in our work, you'll be seeing something like MSB. MSB will be the abbreviation for the most significant bit. And the one on the right, the bit on the right, is the least significant bit. Now, so how many bits are these? These are 3 bits. These are 2 bits. So again, that is very important for us to note. Whenever we talk of a bit, we also know what a bit is. Now let's consider a 4-bit binary number. Let's consider a 4-bit binary number. Let me assume that is this is B3, B1, B2, B1. So this bis would be either 1 or 0. Would either be 1 or 0 because we said a binary number has 1s or 0s. So this bis would either be 1s or 0s. But now, which one is the most significant bit of this? The one on the left is the most significant bit, and in our case is B3. What about the least significant bit? Is the one on the right. In our case, B0 is the least significant bit. Now, so how do we write in decimal? You have this 1, 2, 3, 4 bits. How do you write them in decimal? As we had already said above, this would be B0 times 2 raised to 0. Then plus, this would be B1 times 2 raised to 1. Then plus, this would be B2 times 2 raised to 2. And lastly, this would be B3 times 2 raised to 3. 2 raised to 3 is just 8. just 8. Of course, this is what I'm referring to. So this is just 8b3, and this is 4b2, and this is 2b1, and this is just a b0. That's just a b0. So that is if you're given a 4-bit binary number. This is how you then convert it to a decimal number. An example of a 4-bit binary number is this. When you convert this to decimal, you get 9. Another example is this 4-bit. When you convert it, you have 10. So that is, of course, it will be 8. 8 times 1 plus, this one we said is 4. 4 times 0 plus, what was it? It was 8, 4, 2. So this is 2 times 1. Then plus, this will be 0 times 2, or times 1, 0 times 1. So this gives you 8, 0, 2, 0. So 8 plus 2 is 10. Now, what is the maximum 4-bit? What is the maximum 4-bit binary? What is the largest 4-bit binary we can have? Because we've seen these two examples. We've seen a 4-bit binary has given us 9. Another one has given us 10. What about the maximum? The maximum 4-bit we can have is 1, 1, 1, 1. And this will give us 15. This will give us 15. The maximum we can have is 1, 1, 1. Because how do you get 15 here? This will be 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 times 1. So this is 8 plus 4, which is then 12, then plus 2, which is 14, then plus 1, which is 15. That's the maximum 4-bit number we can have. Now that brings us the knowledge of range that I talked of. So whenever we have a 4-bit number, what would be the range? The least 4-bit number you could have is 0. The least 4-bit number. So if we have something like this, 0, 0, 0, it's also 4-bit. But this, the decimal number equivalent to this would be 0. So that means a 4-bit binary would then range, if converted to decimal, the range would be 0 to 15. So you can never have a 4-bit number that is 16. In other words, what we mean is that 4-bit number would be less than 16. So you can see now, when we convert numbers to binary, we are then able to come up with this notion of comparison. We're able to compare because we know the maximum it can be, if it were a 4-bit number, the maximum it can be would be 15, and the least it can be is 0. So that means it can never be greater than 16. It has to be less than 16. It can never even equal. It can never even equal to 16. Now, so I'm not going to the concept of trying to convert decimal numbers to binary numbers. Of course, I've shown a few examples, and those are enough. But if you want to go deeper into that conversion, you can use this code, and this code can always give you, if you give it a decimal number, it can always give you a binary number. If you give it a decimal number, it can always give you a binary number, and so on. Let me just share this code, and maybe you can look at it later. Just share the code. Yes, the code is here. The code is here. So I want this code to give me the binary number 3. What is a binary? These are decimal numbers. I want it to give me the respective decimal binary numbers. I want it to give me the respective binary numbers. Let's just see. If I say cargo run, what it will then give me. It has told me that 3 would be the same as the binary would be 1, 1. And then 9, the binary would be 1, 0, 0, 1. And then 10, the binary would be that 1, 0, 1, 0. And then this other one, the binary would be this. And then this other, the binary would be this. So what I mean is, if you want to convert decimal numbers to binary numbers, you can always use this code. Because, of course, if I want to change, I can change this 4 here, 3 to 4, and ask it to give me what the binary number 4 is. So I've given it several numbers, it just gives me n of them, all of them. But if you want, you can just give it, can ask for 1. Look at this. 4, its binary number is 100. Notice that 4 is the same as 2 raised to 2. Every number I have 2, every time I have 2 raised to something, then I would have the most significant binary here, the most significant digit here being 1, and then it will be followed by zeros. 1 followed by zeros. So look at this. 4 raised to 2. What about 4 raised to 3? 4 raised to 3 will be 8. So I expect it to be 1, then 3 zeros. Let me just see. Expect to be 1, then 3 zeros. Can go around. Yeah, it's 1, then 3 zeros. What about 2 raised to 4? It will be 16. So I expect it to be 1, then followed by 4 zeros. I don't know whether you're getting what I'm saying. Whenever the power, so the number of zeros will be equivalent to the power. The number of zeros will be equivalent to the power. You can see it's 1, then followed by 4 zeros. So there's something we are getting from there about bits. About bits. What are the bits? How many bits is 2 raised to n? How many bits is 2 raised to n? So 2 raised to n would be n plus 1 bits. But I don't want to go into that. I think I'll go into that next time. But for today, I just want us to stop there. Then when we meet again, we'll now be looking at how to construct arithmetic circuits for binary encoding. So once we know how to come up with arithmetic circuit for binary encoding, it becomes easier for us going forward. Okay, thank you. Let's stop there for now. I will meet on Thursday. Thursday we normally do it from noon onwards.